The last expression that we had dealt was this, that if we define a random variable y equals g of x, then fy of y is this is how we will define the CDF of a function of a random variable, right? So this should be a
Sir,
column. Yeah.
so before that, can you give us the symbols that like showing the PDFs? Like yesterday, we saw that symbol for the triangular PDF. So are there some symbols representing certain PDFs? So can you show them?
I just use two PDFs. So means I just use this symbol. And at times Gaussian with mean mu, variance sigma square, uniform between A and B. Fine. I just use these two symbols.
So these two symbols should be enough for this course, right?
At least for the quizzes where I design the questions.
Okay, sir. Thank you, sir.
Okay. Yeah. So in the special case, I'll just get rid of this. Yeah. Back to the pen. In the special case where gx equal to y has countable number of solutions for all y, fy y equals summation fine. So this you might have done in the previous semester, this expression.
Yes, sir.
Yeah, so this, and now we'll, being done with functions, we'll define operators. Rather, I would make this slightly. So now we'll define operators. So the first operator or operation is the given as, unless specified, I write the expectation operator like this, and this
Sir,
is,
are you writing on the screen right now?
yeah,
It's not showing. It's stuck at g of xi like equal.
okay. I'll reshare the screen. That shouldn't be an issue. Now is it visible?
So it's taking some time.
Okay, let's let it buffer.
Yeah,
Now,
now it's good.
yeah, excellent.
Yeah,
So
now
yeah,
it's
so this is the expectation operator. This I have to anyway delete. So this is the expectation operator. In general, this is called the nth order moment of x, and for any arbitrary function gx, expectation of x. So note that I'm writing capital X on the left hand side, but integrating over small x on the right hand side. For discrete random variables, expectation of x equals summation I xi, probability that x equals xi. Similarly, so based on this, can someone tell me a way to write the PDF of a discrete random variable?
We're using the delta
by using
function.
deltas.
Yeah, by using the delta function. So you already know that. So you figured that out, or you were taught that?
We were
So
taught.
we had a question last tutorial, so I had
L-
to see the method.
Okay,
Sir,
cool.
can you tell?
Yeah, simple. So say I have discrete such that the or 1 to 4 x equals x equal to 5. Fine. So based on this, 1, 2, 3, 4, 5. So let's say half. This is 3 by 4. Okay, let's not do this.
Sir, here PR means probability or PMF?
For discrete random variables, probability and PMF are the same thing.
Okay.
So let's say this is half. This is 3/4. This is something more than 3/4. This is something slightly more. So on. This is 1. So this point. So the CDF will be this, then this, then so will be this, then it will be this, then this, then this, and then finally this. This is how the CDF will behave. Fine. So now if I differentiate this, so the CDF is basically summation k equal to 1 to 4, 1 upon 2 to the power k, u of plus 1 upon 16 u of x minus 5. Fine. This is the CDF. So differentiating this, since I know that the derivative of the unit step is the Dirac delta, df and be written as k equal to k delta Dirac delta plus 16 delta of. Fine. So this is how we write the PDF of a discrete random variable. So this will help us in mixed distributions. You know what a mixed distribution is?
Sir, the thing that we got in exercise, which I guess one of the questions asked about continuous or discrete or mixed.
Yes. So yes. So what is a mixed distribution? That's my question.
So I think we'll be using this deltas also as well as some continuous function also.
Okay. So you don't know that. You're guessing that, right?
Yes, sir.
Mix.
Yeah. Excellent. So let me. So say you have an experiment that I toss a coin. If I get tails, the output is 0. If I get heads, the output, or rather the output is 273. Output is the ambient temperature in Kelvin. Fine. So what I will get is, so the ambient temperature can be a random variable, and it is a continuous random variable actually. So I'll get a peak here. Peak. So with probability half, it will be 273, and then there will be a distribution here whose area will again be half. So this is an example of a mixed distribution. So this is the PDF. You can, this thing can have a CDF as well. This is a mixed distribution. Anyway, coming back.
Sir, can you show the question once?
Question? Yeah.
Just
This one. This is not a question. This is a statement.
yeah, uh, okay, got it.
Okay, great. So now we define expectation of, or we define the variance of x as expectation of x minus expectation of x. Fine. And expectation of ax equals a of expectation of x, expectation of
Sir,
mx.
it is square, right?
Sorry?
E of x
Sir, the
minus
square will be over
x square
the
is whole square.
expectation of x minus
This is a
expectation of
variance.
x whole square. Yes, sir,
Oh,
but
sorry. Yeah.
in the square
Yes,
is
yes,
not
yes.
equal.
Sorry. Yes, the square is over the entire thing. Yeah. Sorry. I'll write it again. This you can show that this reduces to, actually I mixed two things up. You can show this, right?
Yes, sir.
Yeah.
Sir.
Sorry, I mixed these two up, or these two expressions up. So so and you have done these again. This is just revision. So this you have done, right? You know where does the C go?
Sir, a constant function is not doesn't have any variance.
Yes. You know why is that?
because if whatever point we take and try to subtract it from the mean
It's
value,
already the
it
mean.
will, yeah.
Yeah. And generalizing, saying I define the characteristic function of you have done the characteristic function psi of x
So
v, or rather I should do it like this: expectation of j. So this is something like the Fourier transform of the PDF. Fine. Now, what purpose does it serve?
So there won't be 2 pi.
No, no need. You can say omega.
Okay.
Again, what purpose does this serve? That is the
mg.
question.
sir, it helps us to, I mean, in the last course we learned that it helps us to find out certain functions of two random variables. Say the sum of two random variables.
That's a very special case.
Uh,
That is you're talking about the convolution, right?
So the
yes, sir.
moments.
Yeah, this is basically this basically helps us with the moments. So there are two ways of doing this. I'll take the simpler way.
Sir, doesn't this look like the Fourier
mg.
transform?
Yeah, it's it looks like the inverse Fourier transform. So, however, the fun thing is that, or what I use this for, I have actually almost never used this thing, but people use it. So I, so what you do is that you can write this as expectation of 1 plus jvx minus jv square x square divided by 2 factorial, sorry, plus, oh sorry, this shouldn't be j, this should be minus, and again minus j v cube x cube divided by 3 factorial plus, this should be plus, this should be plus, so on. Fine. And I d psi dv or dm gives me a expectation of v to the power, or expectation of j to the power m, v to the power, so v to the power 0, x to the power m plus summation n goes from m plus 1 to infinity jm to the power n v to the power n minus m upon sorry, this should be m factorial divided by n factorial. Fine, this beast. So if I substitute, or
So
if
wouldn't
I
the summation have an x term as well?
x, yes, x, yeah. So sorry, this should be jx. This is jx. This fine. I wanted to write x and I wrote m here. So jx to the power n. This substitute v equals 0. M psi v on dv psi 0 v equals 0 equals xm. Fine, because v is 0, all the other terms and v is always in the numerator, so all the other terms go to 0, or 1 upon j to the power m dm psi x v to the power dv equals this equals expectation of. So we can use the characteristic function to calculate the moments of to calculate the nth order moment of a random variable. Fine.
Sir,
Yeah.
one question,
Yeah.
like we have this characteristic equation to get moments for expectation. Do
Yeah.
we have a similar characteristic equation for co covariances like Rx,
Covariances.
Ry?
So covariances would be defined when you have multiple variables.
Yeah,
So have I, so as I always tell you, have we discussed multiple variables till now?
sir,
So
simple question
have,
because
yeah, I'm also asking you a simple counter question. Have we discussed multiple variables?
no, sir,
Why are you jumping? I'll mute you permanently.
no, sir, no, sir.
You keep jumping 2 steps ahead. This is, consider this as the final warning. I've told you politely multiple times.
Okay, sir.
Don't jump. Yes. So yes. Now we discuss the case with two random variables. Now we can take a step towards answering your anti-causal question. So in case of two random variables, I define the CDF as the outcome. So there's just one outcome, just that now we use two random variables to so how would you can someone give me an example of a single outcome and two random variables?
So roll of two dice
No, roll of two die. Yeah,
together
yeah,
simultaneously.
that is one way of doing this, but we generally consider that as a single random variable because both of them have the same dimension. I would means what I had in mind was more like measuring the temperature and the relative humidity. So at any given point of time, you take stock of the environment, temperature and the humidity. The so actually temperature is a good function for a random variable, or
So
you
meeting of two person at a particular point.
meeting of two people at a particular point. Um, what would you consider as the, or what would you consider as the outcome in this case? The location of the point.
So means there will be a given slot, and if one person comes within that slot, then they will be able to meet. Otherwise, the person who was waiting earlier will go.
So mm, I would say that you have to means what you need to read a bit more. Sorry to say that, but so an outcome would, so that would be a binary valued outcome. So if two people meet, any two people, so the outcome in your case is either meeting, you can represent that by a 1, or a non-meeting, you can represent that by a 0. So there's just one outcome, meeting or non-meeting. Right, Vishal?
Okay, sir.
No, I'm just asking you.
Yes, yes.
Yeah, Bhavnik is saying something. Meeting two people at a point is a textbook example. Yes, the time at which they arrive or the times at which they arrive is are the random variables. I can say that yes, these are so two people arriving at a point. That way, it will be are two random variables. Or similarly, you can say that you drop a coin. You drop anything, the x coordinate, the y coordinate, and the z coordinate. These will be three random variables. That is actually the simplest example, that you take a, instead of a single line, you now take a two-dimensional or a three-dimensional plane or two-dimensional plane, and the x and the y coordinates are the two random variables. So instead of so when you are talking about two random variables, what you are doing is, so I think I should write this. So talking about two random variables are mapping outcome of a random experiment to the xy plane. Fine. This makes sense. Bhavnik, this makes sense.
Yes, sir.
Yeah. Excellent. Yeah. So similarly, Fine.
Yes.
So the properties. First, now this is important. The ordered pair xy lies within an area A of the plane is the plane integral fine, and also f y given x
Sir,
equals.
shouldn't that be minus infinity 2x and
Oh,
minus
sorry. Yes,
infinity
sorry,
2y?
sorry, sorry. My bad. Minus infinity to x and minus infinity to y. So the probability of y conditioned on x, and if the density of y remains did the knowledge of x, then x and y are independent variables. Also, expectation of some function gx of y is infinity dx dy. Fine. If gxy equals xy, then call expectation of xy as the correlation between x and y. And now I can answer that anti-causal question, that if we have, say, if I define
Sir, why is the question anti-causal?
because he asked the question before I defined correlation. That's why I'm calling that question anti-causal. Yeah. So no, that is the correlation. Covariance, I'll define it first. So covariance of x and y is x, y minus expectation of this beast. Fine. Now let us look at another beast. Expectation of j ux plus vy equals double integral xy jux so you can write these e to the power ux and vy as their respective or you can get the Taylor series expansions of these ux and vy's and then do similar jugglery that we did for the single variable case and differentiate accordingly, and you will get a beast that will give you or that you can use to generate e to the power expectation of xm yn. So this will basically you differentiate it n times or you have to differentiate it. So for this, so let me call this psi xy of u comma v. You differentiate this psi xy of uv m times with respect to x and n times with respect to sorry m times with respect to u and n times with respect to v, and you will get the correlation. You will get the correlation, you won't get the covariance. This will give you the correlation, and as the number of variables increases, the monstrosity of this integration will also increase. So actually this is no longer much useful beyond a single dimension or beyond a single random variable. So we can actually define a characteristic function in n dimensions, but I don't think that will be much useful. But yes, mathematically it is possible.
Sir, just now Bhavnik has also asked. Like a correlation, like what we had like learned was covariance upon under root of product of the variance of the two
That is
random
the correlation
variables.
coefficient. So there are
Okay,
three
that's the
things. I'll
coefficient.
just
Okay.
write these names out. So
Okay.
there is something called the correlation. So actually this is slightly confusing. You have to just remember the names. Correlation, covariance, correlation, coefficient. So this we generally represent as Rxy, and this is expectation of xy. Covariance we represent this using Cxy, and this is expectation of x minus x times expectation of y. Sorry. Yeah. Y minus expectation of y. This beast. And correlation coefficient is Cxy divided by Cxx Cxy square root. This beast. This is generally represented by rho xy. So these are three different quantities.
Okay, sir.
So this moment generating function or this characteristic function in m random variables will actually give you access to correlation. You'll have to figure your way out to covariances from that if you want to do that. And in general, using Cauchy-Schwarz inequality, Bhavnik, the problem is that had it been upon me to name these quantities, I would have happily thought of something else. But these are so assuming that you are CBSE
Shouldn't that
student.
be CYY?
CYY, yes. Yeah. Thank you. Yeah. So assuming that those people who have done your class 10th from CBSE, I'm just quoting a reference from your Hindi textbook. I hope that story is still there. तो डॉक्टर चूहानाथ कातर जी का नाम मैंने नहीं रखा था। मैंने रखना होता तो डॉक्टर चूहानाथ कातर जी का नाम मैं कोई साहित्यिक नाम रखता, पर उनका नाम उनके माँ बाप ने रखा था और उसे मैं बदल नहीं सकता था। The same goes for this correlation coefficient. You can want to call it Dr. Chuhanath Katarji if you want. But as a standard, we'll have to use this. Yeah, this and using the Cauchy covariance of x and y is less than or equal to variance of x times variance of y. Fine. So some more results Cxy, actually you can show that is expectation of x minus So two random variables. Now this is also a slightly tricky. So these are also slightly tricky definitions to remember, but you'll have to two random variables are called orthogonal when expectation of xy equals 0. Two random variables are called uncorrelated when covariance of xy equals 0. Fine. And in the special case of Gaussian random variables, you have the case that uncorrelatedness implies independence. Now this brings us to a special case, or these two random variables we can extend a special case that's not in your book, but I feel that is relevant. So I'll just discuss that briefly.
Sir, are uncorrelated and independence two different things?
Yes, uncorrelatedness and independence are two different things. So independence, this is the condition for uncorrelatedness. Covariance of x and y should be 0, or this. So two random variables are uncorrelated when expectation of xy equals expectation of x times expectation of y. Are independent when xy equals fx of x fy of y. In general, independence implies decorrelation, but decorrelation does not imply so you can look at relevant examples from Stack Exchange.
So just one question.
Yeah.
You told about the Gaussian thing, right? If it is uncorrelated, it is independent. We can
Yes.
we can see it through the formula, like fx into fy. We can multiply it and get the same. Is there any other way to see that, like any significance?
For Gaussian, it is through the mathematical expression only,
Okay.
because you can. So the good thing about a Gaussian PDF is that you can define it using the first and the second order moments. So
Okay.
Gaussian PDF is completely characterized by its mean and variance.
Okay.
Whereas there are other PDFs like gamma distribution, beta distribution. There are any function that integrates to 1
Hmm.
can be a PDF.
Okay.
And because of that, there are all sorts of complicated PDFs. So any PDF where you have higher order moments, or any PDF that requires higher order moments to be defined, will not necessarily follow this condition.
Okay.
So for this condition to be satisfied, is the PDF has to be separable in X and Y.
Okay.
Okay. For independence, the PDF has to be separable in X and Y.
Okay.
Okay. So that's why I said that right now, off the top of my head, I cannot think of an example. Yeah. So Adit has helped us. So you can.
Sir. So if a joint PDF, like if two random variables are independent, then
Yeah.
all the moments will be separable.
Yes. So if two
And
random variables are
hence,
independent, in general, expectation of x to the power m, y to the power n will be can be separated.
okay, sir.
Okay. So so yes. Now consider this one special case that's not there in your book, but anyway, since we are at it, let's do it. Consider two random variables x and y, and consider z equal to x plus jy. So now you actually have a complex valued random variable. So this is a complex value. Fine. So how do we deal with this? I think we should um, because for complex numbers we cannot define, so inequalities are not defined for complex numbers, right? So we'll have to deal with this in two ways. So it's almost 4. So I think we should stop here. You have a class at 4?
No, sir, but
No, sir.
Okay, so there's a but, so let's stop here and we'll continue tomorrow.